Alright guys, welcome back from break. We're going to start out with section 5.5, so we're halfway through chapter 5 and sort of getting into the meat of this now. This is theorems about polynomial equations, so if you remember, polynomial is a monomial composed, added, or subtracted together, and we want to, by the end of this lesson, to be able to solve equations using our rational root theorem. You don't really know what that is yet, and to use our conjugate root theorem. Alright, and then here in our little box, we've got the rational root theorem. And basically it's got a lot of math, so we need to sort of break this apart and look at it in pieces. They're giving us some polynomial, and they're saying we have integer coefficients, so that means these numbers out front, the a's, 1s, a zeros, a n minus 1, those are just integers, positive, negative whole numbers. And basically this rational root theorem says we have a limited number of possible roots, which is where the function is 0, the height of the function essentially, the y value. And the first little bullet there says the integer roots must be factors of a0. So if we look at that last term, any of the factors of that, that's possible roots. Then the rational roots, remember rational is a fraction, they have this reduced form, p over q, where p is an integer factor of a0, so that's sort of the same thing as that first bullet, and q is an integer factor of an. So we're sort of putting the last number, the factors of it for p, and then the factors of the first number are our q, and then we put p over q in all those possible fractions. So you can see sort of the example here. They have this 21 and then the 10 here, and then they're factoring each one up completely. So we can see all the factors of 10 are plus and minus because they could be positive or negative, and 1, 2, 5, and 10. And then the factors over here of the 21 are either 1 and 21 or 3 and 7, and then we can do the plus minus. And then they've sort of jumped here a little quick and found out, oh, these are our two roots. And you notice these were in the form p over q. There is a number of, it's negative 2/3. They're using the negative 2 here, and then the negative 3 there is how they got that first one. And then the 5/7 is how they got the second one. And we're going to discuss in a problem or two here later of exactly how they sort of jumped to that conclusion. But that's basically what that theorem tells us, and that's got a lot of good information for us. If you need to pause at any time to write this down, feel free to. All right, first type of problem. We're going to be finding the rational roots, and we want to list all possible roots. So with this one, we're not even going to start out with finding that specific one. We're going to jump around and find any possible one to start out with. So what we're going to do is we're going to start off by listing what our p and our q are. So remember, to get p, we're going to find a0 is 8, and then that an, that's the first one, that's the 3. And p, remember, is the factors of the a0. So listing all factors of 8, we have plus and minus 1, and then plus and minus 2, plus and minus 4, plus and minus 8. That's the only way we can multiply to get 8. So that's all my p's. And then the an, to get the q's, that's nice, it's prime. So we just have q's can only be plus and minus 1 or plus and minus 3. Now if I ask you to list all possible roots, you're going to use that form for p over q. And when we look at the first part here, if I could put like the plus and minus 1, I can put that over 1, and that's why all the p factors are always true. So we have the plus and minus 1, 2, plus and minus 4, plus and minus 8. Those have to be options because that's putting it over 1. And then now we're going to list all of p's over the 3. And so it's going to be plus and minus 1/3, plus and minus 2/3, plus and minus 4/3, plus and minus 8/3. So that's all possible rational roots. If there's any other root with a function, it starts and ends with those numbers, they're either going to be irrational or complex or something other for it. If they are rational, it's one of these options. So that narrows you down. Basically, we had infinite many choices, and we've got it narrowed down to just a few select now that we need to go through and check. All right, now using this theorem to actually find specific roots. So that first example did this all the way. Now we're going to use that. We're going to narrow it down just like we did on the last problem because it wants to know these specific roots. We're going to narrow it down, and then we're going to find specific roots using synthetic division. So I'm going to start off by listing my A0 and my AN. And then I want to go through and list my P, all my possible factors of the A0, and I'm on the next step is I go through and list my N possible factors, or my Q all possible factors of that AN, and so there we go. And then now listing all possible rational roots, we have just the P's will be one choice. So there we got plus minus 1, plus minus 2, plus minus 3, plus minus 6, and then the others are the putting it over the 2. So we have the 1/2. I didn't list the 2 over 2 because that's the 1. And then we have the 3/2, and then I won't list the 6 over 2 because that is the 3. So these sort of get duplicated. I don't need to write them twice. All right, so now we're down, and we've went from infinite amount of choices down to just these select few. And we're going to bring back synthetic division and try it with just these roots. And this is a trial and error thing to where I'm just going for one and hoping it works. If it don't, I try the next one. So setting up my synthetic division. Remember, in your box, we're going to take the number and flip its sign. So right now, the root I'm checking is a -1 root. And then I've listed my numbers 2, 1, -7, -6. That's my coefficients off my original polynomial. And then remember, we're going to bring the first one straight down. And then we multiply the box times the bottom, to get the next number. Then we add down, and then box times the bottom to get the next number. Add down, box times the bottom, get the next number, and then add down. Now, the key we want here is we want this to be a 0. Since it's not a 0, this is not a root. So we tried that one, it didn't work. All right, so move on to the next root. I'm going to try a positive 1, so that means I need to put a -1 in the box. And do the same method. Bring down the 2, and then multiply box times the bottom and keep adding down. With this one, I see I did get 0, so that's what I want. Now, what that tells me is, since a -1 was in my box, I know that x plus 1 is a factor. These numbers left, remember, give me this second part of the factor. So I know I can basically factor that original cubic polynomial into this. All right, and then I can find one root I've got for sure is the positive 1, and then the other one, we need to break that down in either factor or quadratic formula or whatever we can use, and I think Hausstop's going to work nice for us. So I'm multiplying the 2 and the -6 to get the -12, and I see that -4 and 3 adds to the middle. So that's my number there, and I know to multiply to get to the 4, I'm using the 2x and the -2, and then finishing up my factoring. So now I can see that my roots are going to have to be the -1, they're going to have to be the -3/2 and the 2. So I flip all those signs. So that's finding all the specific roots. Now, you might end up doing synthetic division a time or two and it not working, but you just have to keep trying and keep working at it. And that's a tough problem. That's probably one of the tougher problems for this lesson. All right, next up, we've got a theorem here that's the conjugate root theorem. And what this conjugate root theorem tells me is we've got P of x is a polynomial with rational coefficients. Then irrational is the roots of P of 0. Have this form. So now this is stated a little weird. It's saying that irrational roots, all irrational roots that have this form, the key thing is, and I've got a little note here, this is only going to work for our square roots. Cube roots, fourth roots, all those behave a little different. The key is it's got to be in that form, something in a square root. And what this is telling me is if you know one root is like a positive root something, then you have to have that conjugate, that negative root something. So these always come in pairs. And that same thing happens also for complex numbers. Remember, complex are the imaginary. So if we have an a plus bi, you have to have an a minus bi. Those always come in pairs with square roots and with imaginary numbers. So looking at the next problem then, it says, hey, we have a cubic polynomial, so hey, I know it's third degree. It gives me a root of 3 minus 2i, and 5/2 are two of the roots. It says, what's the additional root? Well, when I look, I always want to try to look at these problems and see, do we have imaginary numbers? Do we have square roots in them? And we can see we have an imaginary. So if 3 plus 2i is 1, if 3 minus 2i is 1, 3 plus 2i has to be there. That conjugate pair has to happen. So my three factors are going to be that 3 plus 2i, the 5/2, and then the 3 plus 2i, that conjugate pair. So those are real quick, easy problems. You just got to find those pairs. That's the third. Remember, we only got 5 today, so we're almost there. All right, next type. What quartic polynomial has the roots of 2 minus 3i, 8, and 2? I can see that, gotten a little ahead of myself, that if that's my roots, that means x equals that. So I know for sure that x equals the 2, x equals the 8, and then x equals 2 minus 3i. The conjugate has to also be there, the x equals 2 plus 3i. And you notice that gives me my 4 roots. So what I'm doing is I'm just setting x equal to each one of them. And then I'm going to work backwards here, and I'm going to try to come up with that quartic polynomial. So I'm going to move everything over to one side and set it equal to 0. All right, so we've got them all over equal to 0. And then now I'm going to use that rational root theorem backwards, and I'm going to take all those and make them into one big polynomial equal to 0. We normally do this backwards. So right there, we've got the polynomial. That's it. Now, we don't want to leave it like that. We actually want to distribute and FOIL, however you want to call it, and we want to clean this up. And so I'm going to distribute out the left 2. I'm going to distribute out the right 2. And the right one's really long. And then I'm wanting to clean up this a little bit, combine my like terms. And there's a lot of like terms over here. And then we got to remember that I squared becomes a -1, flip its sign. And so, hey, we've got it condensed down. That went real ugly, and it's back down to not too bad. And then this last one, we got to redistribute out. And this is going to be a longer one also, but there will be a lot of like terms that combine together. All right. So we've wrapped up there, and we can see that this is our polynomial. That's our quartic polynomial that will satisfy those roots. If we type that in like a graphing calculator, we could see the 2 and the 8 would work. Remember, the imaginary roots you can't see on the axis. So that requires a lot of old Algebra 1 stuff, really. All right, and that's the 4th type of problem for this lesson. And then the last type deals with Descartes' signs. And we can see that Descartes was a French mathematician here, and he came up with this method, basically, or this rule that worked always, and he just sort of figured it out, that if the number of positive real roots, P0, let me go up here and sort of highlight for us, positive real roots is equal to the number of sign changes between consecutive coefficients, or is less by an even number. So here we're going to actually like subtract 2. And then the number of negative roots is equal to the number of sign changes of P of negative x. So there's sort of the two differences, or by a decrease of 2. And it says in both cases, count multiplicity, count multiple roots according to their multiplicity. So that multiplicity can be like positive, positive, positive. All right, so it's saying, basically using this now, what does Descartes' sign tell me about the real roots for this problem? So part A, what I'm going to do is I'm going to look for positive roots by using f of x. And using f of x, we're sort of writing it out there, And I'm going to look between one number and the next and see if we have a sign change. And hey, from 2x to the fourth to negative x cubed, we change the sign. Looking at the next one, it changes the sign. And then the last one has a sign change. So we have 3 or 1 positive roots. So I just looked at that function, said how many times does the sign change, and then I take that number or I decrease it by 2. All right, looking at the negative, I'm going to do f of negative x. Now, what happens when I do f of negative x is it flips the sign on the odds only, because the odd to the negative power would make it negative 1, so that's going to flip it. So I'm going to rewrite this function, and you notice all the odd exponents, I changed their sign. And so now the first one does not have a sign change. The second one does not have a sign change. The third one does. So what that means is there has to be one negative real root. There's guaranteed to be one negative. So this sometimes will help us whenever we're doing the synthetic division, that I'm going to focus on that negative root. All right? And part B says, can I confirm it graphically? So what I'm going to do is I'm going to graph it, and using my calculator, and once it's graphed there, I can see that it touches once on the negative side, once on the positive side, and then 2 are imaginary. So yes, it did happen one time negative, one time positive. Now this section has a lot in it, and you might need to watch this a couple times. We're going to get to discuss it in class also. So get you some notes down, get it sort of copied to get yourself a framework, and then we'll talk more about it in class. All right, see you guys later.